Welcome to our November edition of our ACM Chicago IEEE Computer Society Chicago webinar. Hope you had a wonderful Thanksgiving holiday, with family, friends, and refreshed from that much needed break. So tonight we have an interesting topic. We have Dario Dematties. He is from Northwestern University, a postdoc researcher there, and also as well with Argonne National Lab. He will be talking about self-supervised learning at the edge. So you might have heard, self-supervised learning or edge computing. And specifically, he will be talking about addressing label scarcity online. All right, so just welcoming to, first of all, members from IEEE Computer Society Chicago and also IEEE Chicago section. So Computer Society is the Chicago chapter of the IEEE Computer Society. If you're not familiar with this society, we've been doing actually joint webinars for I think the past now like 2 or 3 years now between IEEE Computer Society Chicago and ACM Chicago. Yes, this needs to be updated. We actually now hold monthly meetings now on topics that deal with software, hardware, computing, AI, big data, cloud computing, cybersecurity, and others as well. So I am the chair of the IEEE Computer Society Chicago chapter. Our vice chair is Gina Martinez from Lewis University. We have our website at IEEEchicago.org/CS. And we also are active on our social media. So you can follow us on Facebook, on Twitter. We have our LinkedIn page too as well, our YouTube channel. And if you want to become an IEEE Computer Society member, you can go to computer.org/membership/join. One of the benefits is that you can get discounts for IEEE conferences. So if you're in the space of research and you want to get the latest cutting edge technologies and research and papers, you can register to be an IEEE member, and you can be able to then join the IEEE Computer Society as part of your membership, and then you can attend many conferences at a discounted price, as well as get access to IEEE articles. So if you're a person who reads a lot of particular papers, you can get access to the IEEE Explorer from there. And also as well, welcome to our members of ACM Chicago. So for those who don't know ACM Chicago, ACM stands for the Association for Computing Machinery, kind of similar to what IEEE does. And we are the Chicago chapter of that ACM. So we have done joint events with, like I said, IEEE Computer Society Chicago. I'm also the chair of ACM Chicago as well. We have our vice chair, Mark Temkin, which you see there. He's there in the background. And then we also have Greg Newmark, who is our treasurer. There he is, he's waving. And you can find out all our events from chicagoacm.org. So that's a kind of our landing homepage. We will post our new events there. Primarily, we use Meetup. So if you're not familiar or you don't use Meetup, I would definitely strongly recommend that you go to meetup.com/acm-chicago, register, become a member of Meetup. It's a free membership to become a Meetup member. Join this particular group. This is where we will post our future particular events, and you will see also our previous events that we have had done in the past. We're also active also on social media, Facebook, Twitter, LinkedIn, and all the recordings of our webinars and meetings or so are posted on YouTube. So if you cannot make a particular, meeting or webinar that you're interested in, you can be able to catch the recording. So if you go to the bit.ly/ACM CHI video, you can subscribe to our channel. And by subscribing to our channel, then you're able to go ahead and see the latest videos that we post online, and also see the previous ones too as well. And also as well, if you want to become an ACM member, you can go to acm.org/membership. Same as for IEEE as well. You can get discounts to ACM conferences, and also as well get access to ACM magazines, papers too as well. If you're in that particular space or so, I really strongly recommend that you become an ACM member. And we also as well, if you are a member of ACM Chicago, you can also get an ACM membership as well there if you're not already. And more details on that is on the chicagoacm.org website. All right, so tonight we have Dario Dematties, and I'll turn it over to Mark, our vice chair, to give an introduction to Dario. So Mark, please go ahead.
Okay, thank you, Alvin, and thanks everyone for coming to the meeting tonight. Hopefully you'll really enjoy this. So it's kind of interesting how we found Dario in last month's talk. If you were present at that one, our speaker Charlie Kettler talked about SAGE, and he gave a link to the SageContinuum.org, and I'm looking through this during the talk, and I see sound event detection. I go, oh, that looks interesting. I want to see that, and that's how we found our speaker, Dario Dematties. So he's going to give a talk on self-supervised learning at the edge, as you already know, and there'll be a lot of interesting, we've already seen a glimpse at a lot of interesting slides and videos that you'll get to see in this talk. And currently, Dario is a postdoctoral researcher at Northwestern Argonne Institute of Science and Engineering, and we will turn the floor over to him for his presentation. So take it away, Dario.
First of all, I want to thanks to the Association for Computing Machinery for this great opportunity and the casualties of life, how it happens. Thanks especially to Mark, Alvin, and Charlie for making the origin of this talk. So. My name, as you know, is Dario Dematties. I'm a postdoctoral researcher with a joint appointment with Argonne and Northwestern, and I am working at the SAGE project. And today I will talk about self-supervised learning, why it is important at the edge, how we are going towards addressing label scarcity on online data, collected at the edge. So like kind of a layout of my talk, I will introduce the topic explaining why we think self-supervised learning is important for edge computing, kind of presenting the problems of the current workflow of machine learning for edge computing, presenting self-supervised learning as an appropriate or timely solution to that, but also presenting the challenges that we have in implementing this new paradigm in machine learning, which is pretty exciting. I will show also two use cases in which our group has been working during the last year and is nowadays working on that. First, atmospheric conditions characterizations that we have being working on, and then automatic species detection from passively recorded soundscapes that we are actively working at this moment in that project. Finally, I will, as it is usual, present my concluding remarks. So let's jump in. I will try to explain a little bit what is SAGE. SAGE is a cyber infrastructure of geographically distributed sensors in many states of the US. But each sensor includes cameras, microphone, and weather and air quality stations. Such sensors can generate a very, very large volume of data and provide computed power in situ too, which is the novelty of this kind of sensors. Therefore, fast and efficient analysis is best performed on an embedded computer connected directly to the sensor and not offline. So in summary, our group basically provides a fully functional cyber infrastructure service to scientists who can deploy their algorithms and analyze the data without the need of transmitting it to a central server for prospective processing, but only transmitting the results instead of the data analysis once it is concluded in situ at the edge. So that's a huge difference. And that is provided by our cyber infrastructure. So I will try to go to the standard workflow of machine learning, basically, at the edge, which is this. First, as we already know, a scientist has to find an appropriate data set that is offline or produce its own data set, which is pretty expensive and laborious. Then those scientists has to train the model offline using such data set and validate that model using a holdout data set. And they have to use labels, they have to backpropagate errors, the data set has to have a lot of conditions in order to train properly the machine learning model. And once the model is already trained, it has to be deployed in our nodes in order to make inference. With the weight frozen, it will be making inference while the node is grabbing data. So the model will be with its weight frozen there. It will be learning nothing there, just grabbing information and processing with the training that it had in the past offline. So basically, inference is that the pre-trained model with its weight frozen, as I already said, process the online data and transmit just the results. It doesn't have to transmit the images or audio data, which is heavy or maybe privacy sensitive, but it has to just transmit the data that is the bounding boxes in this case, in this example, with the names of the detections, that it is not violated privacy and it is very, very lightweight if we think in transmitting it to a central computer for faster processing, for further processing. So some of the problem with this scheme of pre-training and deploying machine learning models are the following. The network, as I already said, has its weight frozen on a data set that was trained offline, okay? So the network will have its weight frozen in the node, but it was training on a data set that has its own probability distribution. Yet, the distribution of the online data collected by the node is not necessarily coincident with the original distribution of the data used to train the model. Furthermore, that distribution could vary during time in the nodes as the node is collecting data. This fact or these circumstances make the model inappropriate for processing the online data. Okay, it is easy to understand that. But another important issue that has nothing to do with this is that at the edge, we neither can say not transmit the huge amount of data collected by the sensors. We have to recite that data because the model is not training that. It's just processing the data. It's grabbing information that has to do with the labels of the model that was trained offline. So by applying this scheme, we end up losing a lot of data too that could be of high value for our purposes as scientists, for instance. So the question that we have to make is, can we retain in certain ways such or much of the information collected by the nodes at the edge? So the response that we have and our hypothesis is that we think that we can in the synaptic weights of an artificial neural network trained at the edge. But it is different because it is trained at the edge. It is not just deploying the model with the weight frozen, but deploying the model to be trained from scratch at the edge. But that we are facing a lot of problems with that because it is difficult. So I will not bore you with all the problems that we have at the edge, but one of the most important problems that we are facing right now is the label scarcity. We don't have labels at the edge. There is no labels. Imagine if sometimes it is not viable to label a huge data set offline. Imagine the data that is collected this node at the edge. You cannot label that on the fly. So it is impossible to do that if you want to learn something from the data. So you cannot label that. So the data that you use has no labels. You have to accept that. So we believe, as a group, we believe that self-supervised learning is the solution to this problem. So I will try to explain a little bit how is the standard approach of self-supervised learning. First, you don't need labels to train your model with self-supervised learning. That's a huge advantage. You can use the raw data directly, feed your model with that raw data. Second, for that, you assign a set of pretext tasks that I will explain in detail later what they are. But for now, it is enough to say that they are tasks in which you can assign labels to the data without the human intervention. So you can assign labels to the data at the scale by millions because it is automatic, it is machine. You don't have to put a human or an expert to assign labels to it. So you can use a complete data set with trillions of images if you have the computing capacity to do that. Then afterward, you end up fine-tuning your model. But since the model has been pre-trained, you can fine-tune your model with a very, very tiny or small data set with labels because you want your model to do some task. So you have a very tiny data set with some labels and you can fine-tune the model, but you have to fine-tune. You don't have to train it from scratch because the model have acquired a lot of knowledge from the statistical distribution of the data before. So this is a standard approach, but we use an alternative one that I will describe in detail now. We are not using this. We are not fine-tuning. We are trying to avoid completely human intervention from this, from the labeling point of view. So at Sage, our first approach to self-supervised learning is using our fish-eye sky-facing camera. Basically, what we are doing, we are training a vision transformer to highlight semantic properties from images automatically, without human intervention, without labels, using joint embedding architectures. I will explain in detail all those parts that I am naming now. How a joint embedding architecture actually works. First, we take an image collected by our sky-facing camera and generate two augmented versions of such an image, such as you can think of crop and resize, color variation, shifting, rotation, displacement, whatever you can think that you can do to an image without breaking the identity of that image, you can do that. Second, we fit the same model with these two versions, with these two different versions of the same image. And we eventually obtain two output vectors for the processing, from the processing of those two versions. Well, you will think those are even though they come from the same image, they are different because have different augmentations, but they have the same identity in nature. So the idea here is that the loss function here has to try to penalize the difference or distance between these two vectors, incentivizing the network to produce the same output vector independently of the image augmentations that you use. With this strategy, the network learns to be invariant to any augmentations applied to the input, and with this learns a lot of features, statistical features underlying the statistical properties in the data set. Because no matter how, if you present a cat and you rotate the cat and you change the color of the cat, no matter the color, the rotation, the angle, the size of the cat, it will be saying, oh, this is a cat. This is the idea. So once the network is portraying with sky images like this, and since we are using a vision transformer, it presents important semantic segmentation features of clouds, clear sky, sun, via the attentional maps without the assistance of human labelers at all. Yet, more importantly, the feature vector, the output feature vector of the network presents important clustering capabilities that I will be talking about in the next slide. So, as I already said, the network presents important capabilities in terms of atmospheric condition characterization. First, different atmospheric conditions are mapped in different locations of the network output space. We use a cell organizing map clusterization of such output space, in which we can see that in one corner of the image we have completely clear sky images as in 0D, while in 4A we have overcast images. So we can see that the network clusterized different sky characteristics in different regions of the output space, and the clusterization is working like that. It's capturing different clusters with different sky properties, to say in certain way. But we need to validate that. We cannot just throw visual inspection and say, oh, I swear that this is different, I can check the images and they are looking different. We cannot do that. So in order to validate our model, Sionga Park, that is a postdoctoral researcher working with us, use a unit that is a supervised learning algorithm trained with label data on Sky too, in order to try to predict the percentage of cloud cover of the different clusters in our clusterization. As you can see, we have the same coordinates here, ABCD 0 to 4, 0 to 4. So you can compare easily that if you move from 0 to 4, you will see that the cloud cover percentage increase, and it is telling us a neural network that is state-of-the-art that was trained with human labelers. Yet, we think that information is not only concentrated in pixels that say, oh, cloud, no cloud, that we can say just, oh, the clouds, there are more clouds in this image than in this other image. We have a lot of more characteristics or richer characteristics in the sky that we want to examine in our network, what our network is catching. So therefore, we also pursue the analysis of the diurnal variation of the clouds. This analysis was made by Bhupendra Raut. He is another postdoctoral researcher working with us in our group. Here in the vertical axis, you have hourly frequency, and the horizontal axis, you have the hour of the day from 6 a.m. to 6 p.m. And we can see a very, very interesting phenomenon here. For instance, let me see. In the diurnal variation, we have that in A4, we can see that A4 there is a lot of very early morning night vision images there. Visually, we could inspect that, but if we see this image, is showing a peak here in very early morning. And this is corresponding to this. It is concentrated those kind of images with insistence. So then in row zero, in row number 0, you can see that as you move from right to left, you can see that the blueness of images increase. Yeah, and you can see this replicated in the cloud of points here as you move up in this cloud of point. The image, the skies are more blue. And at the limit, you have in A0, you have a very interesting phenomenon called the blue hour that is used for photographers. And that happened 10 minutes before sunrise and 10 minutes after sunset. And the sky is completely blue and dark, crepuscular-like. And that cluster is catching all those occurrences there too. So other effects that are not so notorious, but there are to highlight. In row number 2, it happened in all the rows, but especially in row number 2, we can see that images, if we move from D to A, from the right to the left, we can see that images tend to be more morning-like clusters and tend to be more afternoon as we move towards the left. We can see that in A2, we have only afternoon images, nothing of, almost nothing of morning images, and this is a gradual phenomenon. We can see that in this D2, we have all the very early morning images, and we can see here in this distribution. So, yet, believe it or not, the diurnal variation is not all. We also have other features captured by different locations at the output space. And this analysis was also conducted by Bhupendra Raut, a postdoctoral researcher working with us. We did the following. We have a ceilometer that is 200 meters away from the camera. And it has a laser that catches the altitude of clouds. So we have in the vertical axis, we have cloud base high, and the horizontal axis, we have the frequency. And we have in the row number 4 here in the top row, we can see that the higher altitude clouds start to dominate as we move from A to D. We can see that we have very low altitude clouds dominating the descent here. And as we move towards the right, higher altitude clouds start to dominate. We have many phenomena here also. Other phenomena are, for instance, cluster. In row number 3, we have cluster 3A and 3B that are mostly cumulus clouds. As you can see, they are catching all the cumulus clouds because the ceilometer is not catching measurements there. Because when you have a cumulus, this is highly likely that the laser that have very low resolution will escape and never return because you have a hole with clear sky there. But as we move towards D, clouds start to be more altostratus kind of clouds, which are thinner layers of cloud, but with more surface of spanning the sky. So the ceilometer will be having a high chance to catching clouds there. And we can see the altitude going high there and with more probability of the ceilometer. So we have many characteristics there to identify. We also have, as I already said, as we are using transformers architectures in this joint embedding framework, this network offer attentional maps, and with that we can segment the clouds in a self-supervised way without human intervention. It is just paying attention to the clouds, and we can send them out clouds or the negative of clouds, and we can see. But not only that, we are in the future, for future research, now we are inspecting the network capabilities to contribute to the analysis of the dynamic of clouds, because we have discovered that different attentional maps are paying attention to different kind of cloud, so we can maybe use cloud vector motions in order to follow different aspects of different altitudes of cloud with different attentional maps. So this is all regarding to our work with clouds. Our next work has to do with self-supervised learning for automated species detections from passively recorded soundscapes. This is our node again, but now instead of collecting images, we are collecting audio data. The idea is to catch bird songs. With that, get the sound wave, and with that, all the information that is in the spectrum of that sound wave. So the idea here is very similar to the one used for the atmospheric conditions. Here, our pretext task is just simply using audio spectrograms instead of sky images. We use a Johnny Bering architecture again, and again we teach the network to be invariant to certain features, such as the position of the bird song in time. No matter how or where is the bird song in the time, it has to be the same bird song. So we teach, we use the same pretext task for spectrograms. I mean, we try to teach the network to pay more attention to the bird song than to other aspects of the spectrogram. As we can see this image, it is paying attention to the bird song, it's highlighted the bird song, even though you have a lot of information in noises and everything in the spectrogram. So if that is the case, if we can make the network to pay attention to the bird song, the clusterization of the output feature space will locate different bird songs in different regions of the output feature space. That is our hypothesis. So I will present a poster I was presenting in Supercomputing 22 2 weeks ago. We can see on the left how, by using attentional maps with vision transformers, we could be able to mask out bird songs automatically without human intervention. As we can see, the typical examples are the attentional map number, the attentional map or attentional head number 3, in which, or number 6, in which the network is paying a lot of attention to the bird song in itself and is ignoring all other aspects of the spectrum, which is pretty important. So that being the case, on the right, we can see how the output feature space distribute different acoustic conditions in different regions of the output space. For instance, we can see that here we have just silent spectrograms that have low frequency noise, nothing interesting. They are clusterized there with high density in the output space. We can see other more interesting phenomena, very interesting phenomena. This seems to be an insect that is in the high frequency of the spectrum. I haven't had time to check that, but I think it is not a bird song, it is something else. I have to check that. We also have other cases with very high frequency, high power noise. What I don't know what it's that, but that is looking very differently visually in the spectrum. So, but more importantly, and this is the key, we can see how the network is capable of clustering different bird songs in different regions of the output space. We have here an example of a common yellowthroat. It is clustered there, just no matter the noise that you have, it is bringing similar bird song to that space. It is clustering also other bird songs. There are, for instance, field sparrow it is very consistent. The network is very consistent clustering this bird song, because maybe it was too frequent, the appearance of this bird song in the data set, but it is clustering very well. But even though the network, I am using another network to validate the bird song, because my network is not telling me, oh, this is the bird song that you are catching. It is not telling me that. It is just telling me this is similar, and they turn to be the same bird song. But then I have to validate that using an alternative supervised algorithm that is called BirdNet. And I have to say that BirdNet has a high difficulty to catching field sparrow, not common yellow throat, but field sparrow. Sometimes it is just not catching very well this bird song. But there are even more curious cases in which our network is clusterizing very consistently some kind of noises of bird song. We don't know for sure what they are, but BirdNet is not, at least in our data set, it's not catching that. It's not detecting that. Sometimes it is detecting the background bird, but it's not making sense of that bird, if that is a bird. So this is the approach that we are following. Now in the next slides, I will show you some examples of videos with bird songs and all the things that our network is clusterizing well. So to start with, we have here a common yellow throat. We will listen it. So there is a lot of noise in the background, but you can see what I mean. It is a common yellow throat, and our network, when you ask to bring similar spectra as to our network from the same region, it is bringing, like, so those are some of the examples that the network is clusterizing. As you can see, the cases, it no matter the bird song is truncated, no matter the bird song is with other background bird songs, it is bringing that bird song. Which is pretty amazing, I think. It is really exciting. Let's go to another indigo bunting. It is also bringing, the network is also bringing together this bird song. I am detecting this bird song with the BirdNet. As I said, I could identify that because of BirdNet, and check in the internet that this is the bird song, because you can look for that bird, and there will be a lot of recording of that bird. This is a field sparrow. BirdNet is struggling with this, because it is too in the foreground. In the background, sorry. But our network is bringing it very consistently. No matter it is truncated, it has noise, whatever, it is bringing it together. So you have a blue jay here. BirdNet and our network both are working really well. As you can see, our network is bringing, it is amazing, because it is bringing not just that bird, but it's bringing the bird at different distances from the microphone. You have there is a blue jay noisy version for the network too, which is the amazing things about self-supervised learning, isn't it? So then we have Eastern wood peewit. If we analyze the cluster is bringing that together too, no matter if there are two bird songs in the same spectrum or not, or this is surrounded by noise. House wren, this is one in which our network and BirdNet are working very well. I think for this data set, This bird is very close to the microphone, and it is in the foreground very clearly, the bird song. So our network was clustering it pretty well too, and BirdNet was detecting very well this bird song too. So, but there are another bird songs that are not catched by BirdNet. I don't know what they are, but our network is clustering them too. So our network is bringing this, and this is pretty difficult. And we can see this is the second one is a bird song that is completely truncated, and sometimes it is truncated by the bird itself. The bird truncates it because it was in danger, it flew away for some reason, but we can see how invariant is the network to bring in topological things that are similar morphology. The network is bringing everything that is similar together. So this is the last bird, I promise. BirdNet has no idea what is that. This pulse like bird, BirdNet has no idea, at least in our data set. But our network is clustering that together, definitely, and very consistently. There are more things to explain here. I don't want to extend it too much. So I want to jump to the end of the presentation. So I will give you the concluding remarks. So what we want is to retain the data information collected by the edge devices effectively and efficiently and at the scale. We want to do that. We want to retain the information. We don't want just the network to be making inference there. We want to learn that. We want to retain the information, but we don't want to save the information. We don't want to transmit it. This is not viable. We want to save the information, save the knowledge of the information in a neural network. So then we want to address label scarcity, dispensing of human in the loop to conduct AI at the edge. That is a challenge. We are trying to cope with that, clusterizing the data, applying different mechanisms and different strategies. But most importantly, we want to avoid human subjective annotations and unleash the network judgment. This is the title that I want you take to home, unleash the network judgment, because the network will realize a lot of things that we as humans, even if we are experts, we could not be able to realize. For instance, there could be certain atmospheric conditions that an expert cannot see in the images that the network can see, and you are limiting the network because you are putting very limited labels like cloud, no cloud, sun, for instance. Or you can see some birds, some noises in spectrograms that are affecting the biodiversity, and you don't realize about that as an ornithologist because you are paying attention to the bird song. So we want to avoid human subjectivity and unleash the network judgment and see what the network is telling us. And we want an interaction between the expert and the network. That is absolutely necessary. The expert is absolutely necessary, but we are potentiating, giving power to the expert with this. We want, in summary, we want to produce a general framework for scientists in which they can use their expertise at the scale. That is what we want to do at SAGE. So I am part of an amazing group of people. I have no words of gratitude towards them. They are helping me a lot to develop my career, and together with them, I never thought to be in a team of so smart people. So I am really happy to be in this team and honored to be working with these researchers and software engineering and everything. I have to say just thank you to them because they are pretty helpful and supportive. So without further ado, thank you very much. And I will leave you with a video of an attentional map following the clouds captured by our cameras. Thank you very much.
All right, great. Thank you very much, Dario. Very, very good and an inspiring talk. I see there's a bunch of questions we have already in the Q&A. So, Mark, can you go ahead and read those out, and we can get Dario to respond. And if you have any other questions, you can also post them in the Q&A as well.
So our first question is, are the augmentations, meaning the rotations and shifts recoloring, are they random for each sky image?
Yes, they are random, and that is an important point. I want to explain a little bit in this because I am talking about getting rid of human in the loop, but even though humans are not assigning labels to the data set, humans have to decide which are the pretext tags, the augmentations that you have to assign to the images or the spectrograms in order to catch what you are wanting to catch in the data set, which is pretty important, but they are random. But you have to choose which kind of annotation, or maybe you can randomize that too, but generally speaking, they are random.
Thanking you for the informative presentation. And could you please elaborate more on how self-supervised learning is used in image segmentation?
Okay, so first of all, image segmentation has to be approached through an algorithm that can highlight in certain ways certain regions of the image, because they are important for the task, for the pretext tags that you are applying to the network that you choose. So in this case, we are using crop and resize, and we are showing to one part of the network a crop and resize and to another part of the network another crop and resize. So the network eventually ends up learning the features of the object that is in the image, that in our case, for our data set, they are clouds. So the network pays a lot of attention to the clouds and to the sun and to the clear sky. So since we are using vision transformers, you have attentional maps. Attentional maps are a constitutive part of a vision transformer. So this network is paying attention to the different parts of the image, and you can highlight the things that the network is paying attention, and with that construct the segmentation. We are doing things like that. I am not saying that you cannot use other architectures, but we are using, we think that those kind of architectures, transformers, are especially useful for these tags and very directly applicable because they have attentional maps. With attentional maps, you can do the segmentations.
Can you elaborate on why the remote sensor needs to do the unsupervised learning instead of transferring a subset of the data back to a server for analysis and classification by a person?
Well, always that you have a person, that person will assign labels. First of all, it will assign labels to a data set. That maybe, it is a hot discussion, but that maybe will inject certain bias in the data set. That is the first thing. We can discuss that in different ways, but there are a lot of papers supporting that humans tends to bias the data set, and the labels that humans assign to the data set is pretty simple. It's too simplistic for the things that the network can assign. Then, second thing, if you train a model, you elaborate a data set, offline data set that you have, put labels to that data set, maybe, and then you train the model and you put the model in the node, frost with the weight frozen. Then maybe the data set that is in the node drift in a certain way, and that will be not captured by the frozen weights of the network. So the network has to adapt to that situation too. And I think self-supervised learning has almost, if you approach self-supervised learning at the edge, you have to solve other problems that I am not addressing in this talk. But if you solve them at the edge, you just have to press a button and say, oh, now train, please. And the network will be updated. And and the network will move its way to the next position of the mean of the current probability distribution. And let's suppose that doesn't happen. You have to do that by hand. If you can do that, you have to do that by hand. You have to label a complete data set every 2 weeks to do that. And we already all know that in most of the cases, deep learning is data hungry. So you will not train a neural network with 2 or 3 labels. You have to put millions of labels in a data set. So there are a lot of aspects that are calling us to change the paradigm and go for something more smart. You cannot label all the data of the universe,
Can the self-supervised learning method be used for scarcely labeled images in object detection also?
Yes, of course. If you have a very tiny portion of the data set with labels, if you have scarcely labeled images, you can use a pretext task to pre-train your model and then fine-tune with a reduced data set. This is a normal approach. But then when you fine-tune the network, you are limiting your network again. So we are trying to go beyond that. We are trying to work together with the network. Let's see a back and forth in which we can analyze the data that the network is throwing and try to correct some, a hyperparameter or something, and try to make a back and forth on that. And there is a model that was given down in last weeks that is called Galactica. And in order to make good citations of text, that model is using a back and forth, it's training with a back and forth with humans. That is the way that humans in themselves are trained. It is not something rigid, it's something fluid that you have to interact with the network. And we are trying to go in that direction with edge computing.
How did you do dimension reduction for ML output to show clustering in 2D?
Okay, this is just for visualization. This is not the real clusterization. The one that I'm showing is just I am using PCA. You can use whatever you want. In the case of cell-organizing map, cell-organizing map just automatically reduce the dimensionality. But all the clusterization is made in the complete dimensionality of the output space. And then for visualization reasons, I am reducing the dimensionality and showing some of the clusters there.
Do you use clustering after you got the results? What is the clustering method that you're using?
Well,
is it SOM?
Yes, that is a cell organizing map. It is a grid of neurons that you have 20 neurons 5 by 4, let's say a grid of 5 by 4, and those neurons are located automatically in the high density of points of the distribution of examples. But every neuron that moves a little bit drift the other neurons that are neighbors to that. It is like a grid that is stretching and trying to adapt to the output space. That is one of them. You can use DBSCAN. DBSCAN was not very good for this because the distribution of point was very uniform. There were not high density, very, very high density concentration of points. So DBSCAN is good for that. So it was not our case and was not working well. So we decided to go for DBSCAN or k-means.
Do you have a fixed number of clusters like k-mean? If yes, how did you decide the number?
Well, that is another human in the loop decision. I am talking of getting rid of human in the loop, but there are many decisions that we have to do, and that is part of the interaction with machine learning. You have to decide that. And the sad point of that is that you have to decide that maybe in a very heuristic way, not very analytical one. You have to inspect your clusters, try to analyze, oh, it is looking better. And then you have to validate that. You can validate that as we did with our colleagues in our group, assigning, contrasting with different methods that are already able to measure the altitude of clouds, or maybe the timely distribution, or the cloud cover percentage. And then you can see effectively that the network is clusterizing something that has some sense. It is not so just visual inspection, but you have to assign that by visual inspection. We were deciding 20 clusters for one of the cases, and for other data set for clouds, and for other data set we assigned just 7 clusters because it looks better, and the analysis resulted well after that assignment. But that's something not solved yet.
Do you perform analysis on the meteorological variables like temperature, pressure, relative humidity?
No, we didn't. We didn't have a chance to do that. It is an interesting point, very interesting point. I am sure there are a lot of correlation between that. But in this first work, it was just visual, only cloud covers with UNet in order to validate that, only distribution, and altitude with the oscillometer. But that's a very good point. We have to do that in the future.
And I have a question. So the noise floor with the birds, what's causing that? And would better microphones help?
Yes, we have not, we have omnidirectional microphones. I don't know very much about that, but they are catching a lot of low frequency noise that I think they are coming from highway, because there is a highway very close to the microphone, and from airplanes. So imagine that's more energy. Most of the energy of the spectrogram is taken by that. But I cut the spectrogram, and I just try to make the network focus on the interesting part for us, that is the person. That is another human decision. But we have to analyze it better, you know. We are in our beginnings. We have everything to run. We have supercomputing to run that. We have all the data to prepare, but we have to start to play with those variables, like saying, oh, if I put the spectrum to that frequency, what is happening? If I filter the spectrums like that, what is happening? We have to try to respond all those questions in the next months. Thank you for the questions.
All right, great. Thank you very much all for the questions for Dario. Let me just kind of share the rest of the slides here. Okay, great. Yeah, so we have some upcoming speakers. So perhaps, Mark, can you go ahead and tell the audience what upcoming speakers we have?
Sure. Well, we don't have a speaker for December yet, but like our slide says, maybe that's you. So let us know. But in January, we have a real surprise. I don't know how many of you are familiar or read the Financial Weekly Barron's, which is from the Wall Street Journal. And I was reading an editorial called A Better Vision of the Metaverse, which is essentially the metaverse is dead, long live the metaverse. And so we're going to have a speaker. I reached out to him, didn't think we'd get someone that high up there, but we did. Is Louis Rosenberg, and he's the CEO of Unanimous AI, which is in Ann Arbor, Michigan. And he's also chief scientist of the Responsible Metaverse Alliance. And he will tell us why, in the long term, the metaverse is very relevant and viable. And that's in January 11th. And we will have something in December as well.
Yeah, that's really great. So I'm sure everybody has heard about, metaverse. I mean, that's what, Meta, when Facebook renamed their company to be Meta, they're betting on metaverse. So this is really great. I think this is our first webinar or meeting in ACM Chicago and IEEE Computer Society Chicago that will be talking about metaverse. So that's really, really great. So thank you, Mark, for helping to arrange that. And like I said earlier, if you've missed any of our past videos, they are all available at bit.ly/ACMCHI video. Subscribe to the channel and you'll get the latest videos that are uploaded, including this one when it's available. And we're always, we're a volunteer organization, so a lot of this stuff, we don't get paid, for doing this. We do this out of our own time, and we want to, help the community. So if you are someone, wants to improve ACM Chicago, wants to get involved, volunteering, and you have skills in writing, or planning, videography, audio and editing, or even like networking to find future speakers. Like for example, how Mark was able to find Dario through Charlie Catlett. And also if you want to help build an interest in computing and just basically, spread the word and, show your passion regarding about, this kind of stuff, please reach out to us. So you can reach out to us at vicechair@chicagoacm.org or chair@chicagoacm.org, and we will go ahead and respond to that. All right, so this ends our webinar. Like I said earlier, this was recorded. You will receive a copy of the recording. It may not necessarily be right away because we do the processing on the recording before we send it, but we also will send a copy of the slides as well that Dario presented, as well as the introduction that I just showed. And if you need to have a professional development hour certificate or so to indicate that you attended this 1 hour webinar, we can also provide that too as well. And I already had opened up a poll, so if you haven't already, please finish up that poll. That will definitely help us to get feedback and to improve and make sure our webinars are high quality and are interesting to our members. All right, with that, I'd like to thanks again, Dario, for your time and your information and your expertise in this topic. So thank you very much for that. And
thank you very much to you. It was a pleasure to be here. Thank you.
Thank you, Dario.
Great, thank you. And also
Thanks,
thank you
Dario.
to Mark, our vice chair, and thank you to Greg, our treasurer as well, for this. And also thank you all, you're the ones that, make us, successful and how we get our webinars and our speakers. So thank you for joining this evening or wherever you are from joining from. With that, so I think we are done. And yep, so thank you very much and have a good evening.